So already as I told, this DC-DC converter design, the types of MPPT techniques, I'll be explaining in first part. Then the operation of SEPIC converter, the design and the simulation of SEPIC converter for this MPPT simulation for this PV system will be explained by my PhD student K. Vikas Verma. So coming to the MPPT techniques we are going to implement, before that the system what we are considering for a PV, when already as I have mentioned, this PV system we can have a two-stage, or if you are having a AC, it is connected to AC grid, and if it is a directly connected to the DC grid, we need a DC to DC converter only. So that's why our single stage connected to AC grid, we have a DC to an AC converter. So where it is trying to, the main work of this converter is to track MPPT, or it will try to track the maximum power. If will, so what is the MPPT controller? So it is not a mechanical tracking. So by using any of the MPPT algorithm, where the algorithm is going to track and give a generate a pulse, so which is going to control this converter, means the duty cycle generated by this MPPT controller is regulating this converter, so that it will give an output, so that the system will operate at MPPT or maximum point, that is the maximum power point tracking technique we are telling. So before coming to the technique, so what is behind it, means, and what are the possibilities of converter, when I'll cover only DC to DC converter. Already I told the options are buck converter, boost converter, buck boost converter, or SEPIC converter, chuk converter, any type of converter depending on your application area or your requirement, simplicity, whatever, what are the, when we are going for this MPPT operation, we will see for that. But coming to the characteristics, what is the, why, means if you see the this IV and PV curve which is merged here. So this is the IV curve, okay. So this is the operating the load line, we are depending on your operating means load variation or operating condition, it will shift between this to this part. But how this power converter is playing a role, means the operating point, how it is changing between this, either this is the PV curve and this is the IV curve and this is the load line. So it switches between this point to this point, means either it moves towards the left or right. So that depends on your how you are controlling your converter, okay. And these characteristics also totally depends which converter you are choosing. So accordingly this load line or the load you have to choose, so that you can will be able to track the maximum power. So here coming to, so three options, so all for three cases I will show you how the load line is changing. So when I am taking a buck converter, for which if you will see the, when I am talking about MPPT control, so what exactly it is, means we are going for a impedance matching, means the load impedance should match with the source impedance. So source impedance, so that is the internal the reflected impedance, you can say internal impedance, or the in DC system you can say it as a simple way, it is a resistance only. So if we, for this buck converter, we know this relationship, the output voltage is equal to the duty into the input voltage, and from that we are getting for a lossless system, the internal resistance is equal in terms of the load resistance is RL by, if we will do this simple calculation, if we will use these equations, you can see it is coming in terms of RL by duty ratio square, okay. So that means if you are varying this duty ratio, so you can vary this operating point accordingly, okay. So if you will see, so if for duty ratio, if we are keeping in this ideal cases 0, that means your input impedance or the input resistance becoming what, infinite, and if it is D is 1, it is D is 1 means our internal is equal to, or the input is equal to the load resistance. So that load line, if you will see, it is varying between this point, okay. It is below the operating maximum point to this side, right side, Okay, and so this is the case when I am taking a buck converter, and when I am changing this buck converter to a boost converter, and in the similar way we are going for a lossless system. For the simplicity, we have taken the output power is equal to the input PV power. So in that case, if you will do the same way, try to derive, you will be getting the internal resistance or the input resistance in terms of the output resistance or the load resistance is 1 minus D whole square into RL. So by putting D is equal to 0, so what is the starting point here? And when I am choosing a boost converter, so the load line or the operating point moves between this to this side, means left side of it. So operating zone is getting limited, though okay, to meet the voltage, to match the voltage, so we are choosing our converter blindly, but accordingly also we have to see in which zone we are operating. Okay, so but second, in the third case, here I have shown because we are going to simulate this SEPIC converter, but same is the case for if we are instead of SEPIC, if we are going for a normal buck boost converter also, you are going to get this relationship. Okay, similar way you can derive, and you can find out the internal R input, R internal, this take it as same because it is same reflected resistance. So here, but what is the advantage we are getting here? We are getting both the operating zones. Means it can move depending on this 0, this d square by 1 minus d square. So if it is 0, so what it is? 0. Okay, so this full, if d is 1, then it is infinite. So it is not limited to, so it is full zone of operation we are getting. Okay, if by varying the duty, we can operate in the full region. So that's why you can go for this SEPIC converter, but if you want a simple implementation, so you can, but depending on, in that case, depending on the bus voltage level, you can either choose buck or boost. So though it is limited to either side, but you can go for that buck or boost converter implementation. Otherwise, the SEPIC or buck boost or a chip converter you can also implement. So this is the operation of it, the design of it will be explained shortly. But before that, I just want to tell one buck converter. I will show one example with the buck converter. Here, this whatever system I have shown just before, 1 kilowatt system, the buck converter I skipped at that point. But as we have taken the 1 kilowatt rating, means it is designed for to meet the load demand of 1 kilowatt. So from there, we have tried to design the buck converter in the normal way. So the design means here it is the, what is the maximum load, current it has to supply, means load current, then the parameters, the filter parameters, the LPV, the output and input capacitance is calculated, okay, by using the usual our design technique, means how to design parameters of the buck converter. Okay, and for this here the current ripple is taken to be 20%, and the voltage ripple is taken to be 1%. So this value is how much ripple you are allowing, that is totally in your hand. So you can make it tight 10%, you can make it 1.05 because may explain with a 2% voltage ripple. So this is means given the design guideline is between 1 to 2% or maximum 3% you can go for the voltage ripple, and the current ripple is between 10 to 30%. Okay, so taking that, the operating range, the duty is calculated to be 0.4 here. Okay, so this is the one simple example I have given, and how it is when you are going to simulate it, the same thing with the buck converter you can simulate. Okay, to get to operate it in the MPPT mode. Okay, or so, but this is the converter design I am talking about. But going for the MPPT, that means algorithm part you have to look for, and when you are going to implement the implement or simulate the algorithm, MPPT algorithm, what are the different algorithms and how you are going to choose the algorithm, and what are the constant or what are the points there you have to see, that we will see now. So MPPT tracking control, if you will give a search, you will get thousands of or lakhs of paper on it. Okay, and that too PV based MPPT, though wind comparatively little lesser will get, but still it is more. Basically, how we'll broadly will divide it? It can be divided into three, and in papers also there are, depending on their requirement, they are giving the classification. Here we have taken from one paper. So this is the classical method, intelligent based method, and optimization based techniques we can tell. And in the classical, we have not till now we have not gone for any intelligent or optimization based technique. Okay, so it has advantages. Okay, it gives better response, but it has simultaneously the computational complexity. It takes more time, means computational burden is more. So we have just focused on this simple classical methods, and there also we are done on the P&O method for the PV system and wind system. Then we have improved it by doing a drift-free MPPT technique by improving it further. Okay, and there we can have a variable step operation, the fixed step operation, that means the step size of the MPPT techniques can be adaptive, it can be fixed step operation. So all these things we have tried one by one. And we have for PV system also we have tried for this INC technique, in incremental conductance method. Okay, this hill climbing and P&O, here it is given a different way, but it is the concept shows it is almost similar. Okay, so because you are perturbing and observing, or you are climbing a hill, it is similar in nature. Then, so this is about the different MPPT techniques available. So how to select the MPPT means when we are going to do the simulation or implementation. So first it is the ease of implementation, and then number of sensor also it is playing a role, giving means how it is affecting the MPPT performance. Okay, the algorithm efficiency, it is not the system efficiency, it is the algorithm means input power to the algorithm and output. So based on that it should be more than 95-96%. We can check it. Okay, so that is also should play a role while selecting the MPPT. And then also cost of implementation, it should be simple to use and implement and also less costly. But if it is like for this optimization technique and the other methods which are difficult to implement, then we are obviously to make our life simple, we are going for our normal, which is a very popular method, that is the perturb and observe MPPT technique. And we are going to implement means already we have implemented for this buck converter, that I will directly show the results, and Vikas will explain you about the SEPIC converter step by step, how to do the simulation, how to get the result, how to go for the how to tune it, those things in detail. So this is the basic P&O method flow diagram. Here how you are moving from either means searching for the MPP point, whether you are in the left half of the MPP part curve, or you are in the right half of the part, depending on what you will see. You will see the change in voltage with respect to change in power with respect to change in voltage. Okay, and the sign whether you are at the left side of the MPP or right side of the MPP, and then you have to perturb further so that you can reach the MPP point. Okay, so these are the very standard stuffs. But to modify it further, we have done one, but here what is the problem with this? This tracking method suffers from drift. Means if there is a sudden increase in irradiance, okay, so this algorithm fails to detect it. Okay, and increase in irradiance in case of wind PV system, and increase in wind speed in case of wind system. For both the cases we have tested. Okay, so it is giving similar type of it. There is a mislead. So to avoid this drift problem, we have modified it by introducing one drift-free P&O technique. So that is, we are also saying it as a modified or DF P&O technique. Okay, so here for both wind and PV system, what I have explained before, we have implemented this drift-free P&O MPPT technique. So here you have added one extra term, so that is whether the change in current. Okay, so that is giving, so in case of drift, So means any change in the increase in irradiance or increase in wind speed constant, this is positive. Okay, so by adding this search means the current information to the loop, it gives a better performance. Okay, so that's why we have modified, and here also initially for the wind based system we have referred this paper. This is also published by our department only in 2015. Now we have done modification and applied the same thing to the wind based system and got better performance. So there also we have published a transaction in power electronics. Okay, so these are the things with slight modification also and improving the performance further. So you can have improve the overall system efficiency and performance. Okay, so this is the result of the MPPT technique having which is applied to the buck converter based system with that PV system I have shown. Okay, this 1 kilowatt PV system with irradiance change, and this is the during irradiance change condition how the MPPT is means tracking. And here one thing previously I have not shown, there in the power performance where we are going for the power management system. So there this MPPT how the duty cycle those things change I have not shown. So you can see clearly this 3-step operation is clearly visible for this P&O technique. Okay, so when you are this perturb and observe, so this gives a but in case of the only P&O means where we are not going for the drift free, it gives the oscillation more power oscillation around MPP. So that also we have avoided, we have improved it, having less power oscillation when we are going for a drift free MPPT technique. So which is compared here. Okay, so it is giving a better result with respect to the conventional P&O. We have implemented simulated the drift free P&O, and it is giving a better performance, and also algorithm efficiency is also improving, which is given in the corresponding paper. This part is also we have published. Okay, so now the session will be taken by my student Vikas Verma. Okay, so he will be explaining the system with the SEPIC converter and in detail. I have just give you the overall overview of the power converter design, the different type of techniques, but how exactly we are going to simulate it, he will be step by step he will explain.
Good afternoon everyone. Today I am going to explain the simulation of the P&O MPPT controller using a SEPIC converter for PV system. So okay, as we know that the buck converter, it will buck the voltage, boost, it will boost the voltage, but in buck boost we can use both stepping up and stepping down. But what is the disadvantage in that buck boost converter is that we are getting an inverted output voltage compared to the input. So to avoid that one, we are going for the SEPIC converter. SEPIC converter, what is the meaning of SEPIC is that single-ended primary inductor converter, where in the SEPIC converter we are extra adding one inductor and one coupling capacitor. So by using that coupling capacitor, you can see that this coupling capacitor, it is placed between the input and output, so it will be used as a isolation between the input and output, which will protect when the load is shorted, it will not affect that to the input because of this coupling capacitor. And also in buck boost converter, the switch is at the input side, so there is some discontinuity in the input current, but here there is no any discontinuity because of the inductor. It is the input is always connected to the load. So what are the main significance of this SEPIC converter is that due to this input inductor, the harmonic low harmonic input current will be there with the low harmonic. So because of that, it will be feasible to use for the applications like battery applications or the renewable applications to track the MPPT. And also when we are using this SEPIC converter in a discontinuous conduction mode, we can use it as a power factor correction rectifier. And also one main advantage also that in PV system we need two diodes. One is a blocking diode and another one is bypass diode. So this bypass diode will be useful to bypass the current which has low irradiations. But the blocking diode is useful to to reduce the effect of the reverse current. So here when we see the SEPIC converter, that there is a one diode, so this diode will be helpful to block the reverse current which is going towards the input supply. So there are a lot of advantages by using the SEPIC converter, and you can based on like if you see most of the applications will see the boost converter for the PV applications, but in boost converter the output voltage is always high with respect to input voltage. But here we can based on our requirement, the SEPIC converter will be used, the output voltage will be controlled. It's a flexible, we can have a flexible control of the output voltage by using the SEPIC converter. So coming to the operation of the SEPIC converter, like when the switch is on, we can see that the input inductor will be charged with this input voltage, and this coupling capacitor it will discharge through this this will charge this inductor, the second inductor, and also this output will be supplied, as there is no connection between input and output, but this output will be supplied by the output capacitor. But when we are going to switch off, when the switch off mode, we can see that the both input inductor and the L1 and L2, the both are supplying to the load, and also this input inductor will charge this coupling capacitor, and both inductors will charge the output capacitor to the load. So this is the operation. We can see that the coupling capacitor will be charged till V input. Because of that, when the voltage across the inductors will be the same. So because of that, we can design the inductor as both inductors in an equal way. So you can see that today we are going to design a SEPIC converter for 2 kilowatt with a switching frequency of 20 kilohertz and input voltage of 100 to 112 volts and output voltage 96 volts, and we are taking a ripple inductor current, and the voltage will be 20% and 2%, and the load resistance based on our formula like V square by R, we are getting 4.6 ohms. So before going to, we have a output requirement 2 kilowatt, but how we will design the PV array based on that. So we have a model these parameters are taken in our college. There is a rooftop is there. So that ratings I consider here. So we can see that we have a 205 watt peak module. So but I need a 2 kilowatt. So how could I arrange modules into array? How many I have to connect in series, how many I have to connect in parallel, and how I make it, how I can meet my required load parameters. So here we are using that to, here our rated voltage is VMPP is 28.4, but I need 96 volts output. So how I can meet? So the output, the number of panels required in series, the rated voltage required is 96 by the rated voltage of each module 28.04, it will give 3.42. If it is 3.42, we can consider it as a 4 module. So we are connecting 4 modules as a series to get our required PV array voltage, required voltage. So but what about the current for 96 volts? Okay, 2 kilowatt. So how much current we need? We need a 20.833 8 amps we need. So for that, but here our ISC is 7.9, maximum current is 7.91 amps. So how we can connect these strings, this series? We call it as string, means the panels modules which are connected in series, that will be called as a string. How many strings that we have to connect in series in parallel to get the required current? So we can see that number of PV strings is the rated current by ISC of the module. That is, our rated current based on our 2 kilowatt is that 20.833 by 7.91. It will give 2.633. That nothing but 3. We consider as 3. So we have to connect 3 strings in parallel to get the desired current. So you can see in that short circuit current is 3 into 7.91, 23.73 amps. So by this we can meet by using 4 models in series, and strings connected in parallel is 3. So by using this configuration, by developing this array, we can meet our rated output. rated output power. So how much power it is generating? So it is not exactly giving 2 kilowatt, but based on our modules connection, it is giving around 2.47 kilowatt. Because of that, we can see that 2.5 into 4 into 3. So we can get 2.4 kilowatt. This is the maximum peak power that we are getting from our array. So with this design, PV design, we are going to calculate our what are the duty, how much duty ratio it should be operate, what are the filter designs that we have to consider. So here we can see for this was done for the continuous conduction mode. We can see that we have to find at what range, because PV is not a constant power source. It is depending on the nature. So based on the insolation levels, the operation of the PV, the peak power will be changed. So based on how much we can consider, like I considered the voltage window from low voltage to high voltage. That voltage I take it as a 75%. So that 75% of my rated voltage of my array will be 84.45. So this is the minimum voltage that I am considering from the PV module. So by using these things, I have to find what are the duty ratios that I have to will be available. Like what is the minimum duty ratio, what is the maximum duty ratio that I will be considered to get my desired output power. So here we can see that the same as the buck boost converter, like we can see that D is V0 by Vin plus V0. Nothing but when we consider it as in terms of V0 is equal to Vin into D by 1 minus D. So we can see what is the minimum D will be available at when there is a maximum voltage. So our maximum voltage is that 142.2 volts. The maximum voltage of the array is the 142.2 volts. So with when is there maximum voltage, our duty will be minimum, and when is there minimum voltage, our duty will be maximum. So here the D minimum will be 0.4040 and the D max will be 0.5332. So where we will use this D minimum, D max, why we are using it? This will be useful when we are designing our filter parameters. So coming to our inductor selection. So we are taking L1, L2 is equal, because I told you like the voltage across throughout the switching cycle, the voltage across the inductor will be the same, because you can see that when switch is on, this voltage will be V in, and when the inductor is this coupling capacitor will be charged to V in when switch is off. So that only it will be this voltage will be appeared across this L2. So the both voltages across the L1 and L2 will be same. So that's why we are taking as L1 is equal to L2. So why we are taking V in minimum? Because at a minimum voltage level, the peak current will be is more compared to V in max. So that's why we are considering a V in minimum voltage. At V in minimum, our duty cycle will be max. So that's why V in minimum into D max by delta IL into FSW. So our delta IL, we consider it as a 20% of our, the IL is a input current. So we know that our input current is 23.73. So based on that, the delta IL is 20% of the 23.73, it is 4.746 amps. So by using this thing, we are getting our inductors L1, L2 as a 0.474 millihenry. But in a SEPIC converter, there is one more advantage, is that we can reduce the size of the inductor. Here we are using separate inductors, but if you use a coupling inductors, then our inductor value will be L1, L2 by 2, means 0.474 by 2. It will be because of that coupling inductor. So like that is also one of the advantages of the SEPIC converter. If you use a coupling inductors, our size of the converter will be reduced. So the inductor will be reduced. So what about the coupling capacitor? This coupling capacitor, we can using that I0 into D max. So why we use D max means like at the D max, the maximum output power will be applied, because more output voltage will be there. So based on that, we have to design our parameters based on our require, like high voltage, like so D max will be because the maximum voltage will be there at D max. So that's why we consider this as D max. So by using this formula, we are getting our coupling capacitor value as 327 microfarads, and the output capacitor is also same, but here we are using divided by 2. So our output capacitor value is 576 microfarads. So these are the parameters which are designed for our rated 2 kilowatt and 96 volt DC bus. So these are the general steps to build the simulation model. So now I will I'll simulate. I'll show the how we can simulate our SEPIC converter. How we will based on our design parameters, how we can construct a SEPIC converter, and how we can build a MPPT controller for that to get our desired output. So here, as we know that how our so by the steps that we are using here is that first we will create a new model in a simulation. Simulink model that we are going to design by using the blocks which are predefined in our Simulink model. So we can first we have to create a new model one by one we can. So Simulink model. So after that we created one new Simulink model. In that we have to find the blocks, which blocks we have to use. So what are the blocks we required? One is we need a PV panel, and we need the filter parameters like inductors, capacitor and resistors, and we need a switching device, active switch devices, IGBT with body diode and one diode. So these are the blocks that we required to construct our model. So in that where we can, there is a library browser. So when we click on this library, it will be library will be open. So when we go to Simscape, so here Simscape electrical, in this specialized power system. So in this, when we click on sources, so there is a PV model, add to block. See, this is the PV array, PV module. This is a model. This one we have to make it as an array based on our requirements. So when we double click on it, so we will get the block parameters that we have to design here. So this is the parallel strings. So how many strings that we designed here? How many strings we required? So we required parallel strings, 3 parallel strings and 4 modules. So 4 series modules. So we have 3 parallel and 4 modules. So but our power is 205 watt peak. So here we have to give our array, our VOC and ISC and VMP IMP. So our VOC is 35.55 and VMP is 7.91. And our and VMP IMP is 28.04 and 7.31. So when we click apply, 35. Okay. So when we click apply, that watt peak will be changed around 204.972. So we got the required module. What are the parameters which we required? That module will come. We will get here required. So so we are here. We are using only by changing the irradiations. What is the characteristics of our PV model that we are going to design. So we are making it array at the rate 25 degrees centigrades and specified irradiations. By clicking this, the temperature will be same, but the irradiations will be we can vary the irradiations. So after this designing of PV, we have to get the switches. So we need a IGBT module with body diode. And we need one diode. We need a diode. So we got the switches. Now we have to go for the passive flux RLC branch. So we need 3 capacitors and 2 inductors. So by clicking on this, we need a capacitor. So the capacitor rating will be input capacitor. We can give anything. So this is the coupling capacitor. So what is our design coupling capacitor? Our coupling capacitor is 327.9 microfarads. So microfarads, and we need an output capacitor. That one will be output is 576.9. So we got the capacitors. Control R. So now we need an inductors. One is just by changing this, we can get inductors in only RLC branch. We can get all the parameters. So what is our L1? L1 and L2 will be 0.474. Our L1 is 0.474 millihenry. So both L1 and L2. So now we are going to connect this thing. So to sense the voltage and current, we need a voltage measurement and current measurement. So our input will be connected to the what is the input current based on. So after that we have an input inductor. One by one. input inductor, and it is connected to the switch, as we see here, that as you see our diagram. See, input is connected to an inductor, and then that inductor secondary is connected to the collector of the switch, and also and one of the and the input connection of the coupling capacitor. So coupling capacitor, then inductor. This coupling capacitor will be connected to inductor and the diode. And this diode is connected to. So we have to connect the load. So our load resistance is 4.6. So R 4.6. Yes. So this is our converter. So now we have to know what is the how the input from the PV, how the input voltages and how the input voltage and current and how is the power is varying. We have to check it. So for that we have to connect the sensors. Already connect the sensor and this voltage sensor. And also we have to check our output voltage and output current. So for this we have to check in the scopes. So in this you can get scopes. You can see the commonly used blocks, or you can sinks, and we see the sinks simulink. In simulink in simulink block we can go another pre-blocks, that is in sinks we can get the scope. First of all, before going to scope, we have to check the input and output current. So for that we are using a go to and from blocks, where we can make it as a proper model. So these are the go to and from. So go to, this input current will go to this go to block. So we will name it as this is an IPV. Right, and another one we need one more go to. It will be VPV. So to get the power we have to multiply this IPV and VPV. So this in Simlink we can get in math operations. In math operation we can get this product. So we got go to, this is a go to block, but from this we have to take it. So we have to use from block. From block, which one? So what are the initials you have gave for that? You have to give the same, then only it will take from that. So it will be again, we will use go to for this to keep it as a this will be PPV. So now we got this one. We are going to measure the IPV, VPV, and PPV. Now we are going to use the same go to and from blocks for this I naught and V naught. We need so we constructed our model also. This one. So we have to calculate the output power also, how much we are getting. So for that we have to this one also we have to give it to the product. To get the P naught. So we have to check what are the things. For that we have to double click on the we have three parameters. One is VPV, IPV, and PPV. So for that, if we double click, we can go for the configurations. There we have to give 3, and the layout be 3. Apply. So we can see all the 3 parameters here at a time. For that, so we have to give the from blocks. We have to connect to the scope. And, like that only we have to check that I naught, V naught, and P naught also. Okay, now it was done. We connected PV with CPIC converter, but first we have to give the rating, like what are the insulations, what are the radiations that we are going to provide. So for that we need at a different installations how it is working. To check that one, we have to go use the signal builder. We can see this. The signal builder. So first we will check with the 1000 watt per meter square. And with the temperature, our temperature is around 25 degrees fix. So now we have to develop MPPT. So for that we have to write a code. So for that we need a MATLAB function block. So this is the MATLAB function block where we can write the code here. So it's already there is a predefined code. So you can see that. So this is the P&O MPPT algorithm code where we are our output required is a duty. Our input is VPV and IPV. This VPV and IPV we are getting from the sensors which we are used as a voltage measurement and current measurement. So we are using is a delta is a 0.02. It's a step size. So at what rate that it should change its steps. So based on this delta, the oscillations will like if you give more delta, it will take more time. Like the step will be more. So if the step will be more, what will there will be a chance of missing the MPP. So we should design it in a proper way that our delta should be reasonable, that it should find the MPP point. So this is algorithm where we see in the flow chart. Previously, as madam told that. So this is the MPPT algorithm which we developed as a code in that MATLAB function. So so as we develop the code, and then we have to connect the VPV. We have to take this VPV from here as a from go to from block, and then IPV is here. For this we need to like our duty should be in between the 0 to 1. So we should keep in saturation block. Continuous saturation block. So this saturation block to our should be in between the range of 0.8 and 0.1. Our duty should be, so from this saturation block it should go to the PWM generation. So in this This PWM generated DC DC, can use this one. So this one we have to go switching frequency, we are using 20 kilohertz. So 20 for 3, and the sampling time will fix it. So this one it will go to the switch signal. So we have to take one more from block, go to block. We denote it as S, and this go to will go to the switch. So it will become a from block. Yeah, now we develop the MPPT also. Signal generator. So we can see here so this is the developed MPPT. So, so it's a signal builder which is used to give radiations based on our time. So I gave as a 30 seconds. If we can change it, like when we go for axis, change time range. If you want to 10, you can give 10 seconds or 20 seconds, whatever you want. I'll give 20 seconds. Okay. Then if you want to change the range, I gave from 0 to 6 seconds, my irradiation should be 1000. From 6 to 12, my irradiation should be 500. And from 12 to 20, my irradiation should be 800. If you want to change that one, you can change. If you want to keep this one as a, you have to click on this. And if you want to change here T and Y is there. So if you want to change to it is a 600, you can change. So it went to 600. So like that also, if you want to change the time, you can change. So this one it is at 6. So if I want to change it to 5, so it will go to 5. So like that we can use the signal builder to give the signals regarding our requirement. So presently I am keeping it as 6, and this one is 500. So this is my signals that at different irradiations how my this converter and the MPPT is working. So I have to say, and one more thing is that this power guy. This power guy is important when we are using the active switches. So this power guy here, when we are using active switches, we need this one. So we have to choose whether we should be continuous or discrete. So I am using as a discrete, and I am using a sampling time of 1 micro. Okay, and I am running it a variable step or fixed step, but I am giving it as a fixed step. And this is a different kind of solvers. We can use any solver. I am using this ODU 45, and this ODU, then apply. This is a fixed step. So this is a fixed step size. I will give micro. So now my converter is ready. So now we have to run it. So but what is the peak power? What is the peak power of this module? So at 1000, at 500, at 800 watt per meter square, what is my peak power? How we can check whether it is tracking or not? See, if you see here, see, if you click on this PV module, here irradiations it is showing 1500 and we are giving 800. Whatever it may be, you can give any irradiations. 1500, 800 I gave. So I click on the plot. So we can see here that what is my peak power here. When at 1000 watt per meter square, my peak power is that 2.459 kilowatt and my voltage is 112.16. So this is it should be tracked. 2.45 should be tracked. And also at 800 watt per meter square, 1.9 kilowatt is my peak power. And at 500 watt per meter square, 1.25 is my peak power. So these are the peak powers that it should track. We have to check. So whether it is tracking or not. So we can see here, see the peak power. See around 2.45. See, these are the oscillations. Like what are the disadvantages of P and O is that there is an oscillation around the peak maximum power point. So because of that we are getting these steps. Because of that delta D, if you optimize the delta D, we can exactly get the without this drift will be reduced by optimizing that. So for 1000 watt per meter square, my peak power should be 2.4 kilowatt. As we see here. So you can see that 2.459 kilowatt, but at 500 1.259, it should track 1.259. So it is tracking 1.259 at 500 watt per meter square. So from 0 to 6 I gave 1000, from 6 to 12 I gave 500, and from 12 to 20 I gave 800 watt per meter square insulation. So when the insulation is changing, my MPPT should track. So at 800 watt per meter square, my MPPT should track 1.98 kilowatt. So when we come, so it is tracking around 1.98 kilowatt. And also my output also. So this is my output. As it is a raised to load, so whatever power it is drawing, it will deliver to our load. So to maintain the constant power, like we should use the a battery connected to this PV. It will maintain constant voltage and a constant power regarding based on our loads. So if you want to, so I need a 2 kilowatt. I need a 2 kilowatt, but it is generating 2.5 kilowatt. So how I can get 2 kilowatt? Or you can make it as an off MPPT, and you can use a controller to make constant power. Here I am using only constant load 4.9, but all the voltage, current and power, those are varying. If you want a constant power, then you have to use any controller, and you have to use this MPPT as an off MPPT. So at each installation, so how my duty is varying. See, we can see my duty is around 0.5 when it is 1000 watt per meter square. and when it is at 500 watt per meter square, my duty is around 0.42 like that, and then when it is at 800 watt per meter square, my duty is around 0.47 like that. So based on the insolation, my converter is changing its duty cycle based on the insolation, and based on the output, my converter is working and it is tracking the maximum power point. So these are the blocks which I use as I show you. These are the blocks. This is the model which we developed in the simulation. So these are the results which we can see that the maximum power point tracking in each and every installation, 2.4, 1.2, 1.9 kilowatt, and the respective duty cycles based on the power level, power which is available to track that one, that the duty should also act, because it should match the that output impedance to the input impedance. So as that is the rule of this maximum power point. So to match that one, our duty should be act based on that. So this is the PV voltage when it is at maximum, and this is the PV current. So when the insulation is changing, the insulation is directly proportional to the current, maximum current. So when insulation changing, that current will also change. So we can see that at 0 to 5000 watt per meter square, the current is more, around 24. But when it is at 500 watt per meter square, it is around 12 amps. And when it is at 800, when it is increases, again the current is increasing. So that you can see, and the voltage, you can see that it is almost same. Because voltage is not directly proportional to this insulation. It is so that's why it is not changing that much, but the voltage is sensitive to the temperature. When you change the temperatures, this voltage variation will be there. So these are the results for at different radiations, whether my MPPT is tracking or not. So these are the assignment questions. So for this CEPIC and also the design of PV converters. So please. So these are the references. Thank you. So if any questions, you can ask. So okay, if not, we can close this one. So don't forget to do this assignment.